Hey, hello everyone. My name is Tanya Sailabi, and I am the moderator for this session on travel behavior, choice, and demand analysis. So, in this session, we have again 6 presentations, and we have roughly 20 minutes for each presentation. So, we will have like 15, 16 minutes dedicated to the presentation itself, and then we can have 3, 4 minutes for each of the talks for Q&A and ask questions. So we will begin with the first one with Renato and we will learn why are people moving. So are you ready?
Yes, I'm ready.
Okay, you can begin.
Okay. Hi, everyone. You're probably wondering what is happening in these pictures right here. This is a typical way in the south of Chile, in a specific region, to relocate yourself. When the people wants to relocate
Uh,
themselves,
Sorry, Renato. Oh, okay.
tell me,
Your
you see?
presentation is now on. It wasn't before. So
Ah,
you can
okay. So
continue.
in this picture, we can see a typical way in the south of Chile that the people relocate themselves by moving the whole house. So if they want to move from one place to other, they can move with the house, and with bulls, they drag it, they pass it through rivers. It's a whole experience. So it's easy to see that here a relocation occurred because we see the house moving from A to B. But how can we do the same analysis? How we can say that a person relocated by using other data? So we did this study called Why Are People Moving? A temporally validated detection of residential relocation and its urban drivers using smart car data. Residential relocation is one of the fundamental factors that determine the economic structure, transportation systems, and social development of cities, and is a key factor that the urban planners and the people that create the public policies have in mind. One of the problems is that periodic surveys do not allow for continuous analysis of urban dynamics. For example, in Chile, every few years, people go house by house, asking who lives there, and they can compare if the same person is living there like 4 years ago, or if it's a new family, and there they can move the changes. So this is a problem because if we do this static, we can't see the dynamics of urban movements. So for a little bit of context, this is Chile, this long and thin country. This is Santiago de Chile on the right, is the capital, and 7 million people live here, so roughly 38% of the country, and is divided in 32 communes. So, as public transportation network, we have an integrated fare system. With the same card, you can pay the metro and the bus. We have 6 metro lines, and there are 2 coming soon in 2028, 2030, we hope. And we have a dense bus network that covers the whole city. And it's something we are really proud about. The smart card data, we have a tap-in based system. So only when you board the metro or the bus is that you tap in. And that makes that only the boardings are observable. But the alignment points are estimated. This was studied in 2012 by Munizaga and Palma. They proposed a method, and is what is used today to estimate the alignment point. And we have a high evasion rate. It's a 40% of the users, but although the estimations can be corrected. So, for residential relocation estimation, in 2018, Amaya, Cruzat, and Munizaga created a method to use 1 week information of the transactions to determine where a person lives. So the method works like this. They take the first transaction of every day. We suppose that is the transaction that they use to leave their houses. Even they analyze and they say that 3% of the whole transactions in that period of time is people that is coming back from home because they have night shift. So it's only a 3% of people that is not going out of their houses. And they take the first transaction and they say, okay, if these first transactions are all within a radius of 1,000 meters between each other, we can say that the geographic midpoint of all these transactions will be the center of where you live. And so they draw a line of 1,000 meters and they say, you live in this circle. Inside this circle, you live. And this method was validated, and it gets a 70% of accuracy. Here we have a diagram. I don't know if you want to take a photo. It's the generalized method and is parameterized. And in the paper they studied, and they say that we're going to ask for 3 transactions on each week for every card. And we're going to ask them to be between 1,000 meters. Those are the parameters that work the best for this method. So the extension that we do is, okay, if we have a larger data set, that should allow us to observe individuals changing their location. Because if we have each week, we can apply this method each week and then see how the people is moving. So the motivation is that we can analyze how people explore new routes and adapt to a new choice context. That was the first motivation of this job. That was, okay, when the people change, how much they take until they can establish a new route. But we found that the only question of why the people was moving was an interest question by itself. There's a previous study that was made in Beijing that they use only metadata and they use only 2 weeks, was before pandemic and after pandemic. And the location was associated to a metro station. So this will be one method that we will analyze and see how it works in Santiago de Chile. So the research objective is that we can infer a residential relocation in Santiago by extending this method and comparing the one that they use in Beijing. And we will determine the urban and socio-demographic characteristic of the areas experiencing population growth or decline. So the methodology was that we have 5 months on transactions disaggregated at the trip level. So we have more than 3 million trips per day. And we also have urban data and socio-demographic data. Here we have a table of the data. We have 17 weeks continuous. And we can see that we have 21 million transactions every day, 70 millions. And every day we have around 2.3, 2.5 unique users of the transport system. And here we take the same week that Amaya used in 2018, and we compare her method with our data. So we get similar results. The same method that is validated at 17%, we applied it and it works well. So we saw these numbers and we remain calm that we were not inventing anything new. We have the urban data. We have here every red point is one transaction, so we can see that builds again the whole system. We also have the bikeways per kilometers. So we can characterize this whole city by using hexagons, and we say how many kilometers of bikeways are in these hexagons, how many bus stops per hexagon, how many metro stations per hexagon. Here we have, for example, up here the green area, so we can see how much of the hexagon is green area by using satellite image. And etc. We have is to show a large data thing. So the methodology is, okay, for each week, let's apply the method that we saw before of the transactions that are within 1,000 meters, and let's establish a baseline cluster. And this baseline cluster, we have to meet some criteria. The criteria that we use is that the cluster has to be compact. We don't want, like they did in their paper, we don't want that the transactions in the beginning are too far away. So we ask again 1,000 meters, like Amaya did. Also, we say, okay, there is one location that is more than 1,000 meters. Okay, let's keep that in mind and let's see what happens when that person moves more than 1,000 meters. So we see, okay, if the person moved more than 1,000 meters, did that person stay at least 3 weeks in the beginning and then stay at least 3 weeks in the new place? So we call that temporal persistence. Are these two clusters separately enough? So we call that intercluster separation. And is this final cluster compact? That means, did this person move again a third time? If that's the case, when we discard it, because it's not probable in 5 months, we say that it's not factual that they moved 2 times. So by doing this, we can remain with cases that we see that are reasonable that a change occurs. I'm sharing the whole screen, right? Or you see only the presentation?
We are seeing your
Okay.
web browser.
Okay, here we have an animation that we can see the movement of the people, like in real time. So each point, 1 week that a relocation allocation was identified, and we can see how the people is moving. So for example, we choose this one randomly. Week 5, week 6, week 7, and week 9 jumps there. 10, 11, 13 is moving around, and we can see the person moving. So we can look this and say, okay, it's probably a relocation. Okay, so here we have the results. We see that 2.7 million of residents was estimated. And of all those 2.7 million, only roughly 3,700 residential relocation. That makes up to 0.13%. Here we have a map of how the people was moving. So we can see that there is in the center areas really red, that there is people going out, and we see areas really green, that is people going there. And here the method allows us to describe the whole patterns. So we have relocations, the number that we said before. We have a stable resident pattern, people that didn't move. We calculate the location in the beginning, and they stayed there consistently. And we have people that have transient patterns and errors, and that allows us to decompose which errors are. So for example, no baseline cluster. These people appear separately too much time, so we say, okay, we don't want to deal with these people because we don't know if this is their established residence. There's no final cluster, so they jump more than 1,000 meters, but then we lose them of the database. Maybe they change house and they change transportation mode, or maybe they did another thing, so we don't want to deal with the people neither. And maybe there's a double relocation that is not factible, we say, in 5 months. And round trip movers is that they were in the beginning, in their initial cluster, then they jumped 1,000 meters another week, and then they came back. We don't know what that people did, but we can't say that was a relocation. So if you remember, we talked about Beijing. The Beijing, they use only 2 weeks, pre-pandemic and after pandemic. So what happens in Santiago if we take 2 random weeks? Well, if you use 2 weeks and we say, okay, in week 1 you were in A, and in week 2 you were in B, then it's a relocation. Okay, and if we do that, we jump from 3,700 to almost 15,000. But what if we look the week after? So we have 3 weeks now. We say that you change, but what happened the next week? We get that 5,500 people came back to the beginning, and 400 people moved again in 3 weeks. So if we only use 2 weeks, we can't say that there are relocation occur, because we get almost 40% of false positives in a case like Santiago. And when we do an economic model, because we have all this urban data, and we try to explain why the people is moving by using the total station, the bike weights, the hospitals, and the house prices that we found that they're endogenous. So, but first we need to correct this endogeneity by using instrumental variables. So we have the house prices that are correlated to other things. So we correct it by using the average neighbor house pricing that this is studied, and with the average income of neighbor areas. And when we do this analysis to try to explain why the people is moving, we get results that are consistent with the cultural and social context of Santiago. And of course, this is transportation people. This is users of the public transport. So we see that people is willing to move near the metro. The metro has a positive effect. The people is wanting to move to the metro and green areas. The interaction between these two things. And we get consistent with the literature that the dwelling price has a negative effect, and metro and dwelling price has a negative effect too. So that's the economical thing. But what happens if those relocations that we used before, like the Beijing method, we run the same analysis? We get things, for example, metro stops being significant, but if we do it with 10%, we will get that metro is negative, something that is weird with the data that we have, like it's people that is using the system even after moving, so it's weird that we get a negative thing. And the dwelling price stop being significant, something that we know it can't happen because the dwelling price has a negative effect in the relocation of the people. So this means that it's not only a 40% of false positive like we can see with the eyes, but it also makes that the economical analysis stops having that much sense. So the conclusions is that based on a Maya past work and the Beijing case, we propose a method that identifies location changes considering the stability to make inference. We show that if we take out the temporal persistence, we get economical results that are not according to the literature or the reality of the place, like Santiago. And the transport people is leaving the center in Santiago, opposite what was happening in Beijing. And of course, we have to recognize limitations. This is only stable transport users because we are asking them to keep using the public transportation system even after moving house. And we don't have crime data available that we think it can be an important factor to decide the new house. Thank you very much for listening, and any question I will be ready to answer.
Thank you so much. Do we have any questions from the audience?
Here in the chat, there's one, huh?
Yeah, we have one question in the chat box. So for the no baseline cluster and no final cluster groups, do you think those mostly reflect real behavior complexity or limitations of the clustering rules?
Yeah, there's some cases that people disappear after we mark them like, okay, you relocate yourself and they disappear of the database. So we suppose that is people that change house and maybe change transportation mode. So instead of using the public system, now they use bike. Maybe they're closer to the job, or maybe they change further and they're using car. So we think that is really a really interesting question to analyze the behavior of the people. But of course, these rules that we use were like constructed while we were doing. So of course, there can be a space to that is a mistake of building these rules.
You also mentioned somewhere that you are considering 17 weeks. So
Yes.
that is about 4 months. Are you also considering other effects, like does things like change in the season or things like that are considered in your like study? Or are
Yes,
you going to?
we chose those months because in Chile between March and July is a stable month, but September is the national holiday, so people disappear, and January and February is summer, so people disappear too. So those is like a continuous space time that we can say, okay, people is actually working here. Like a fun fact, we did the same analysis in February. So in February, people is on vacation. So the people that is using the transport system continuously is people that is actually working. So we can make a lot of more residential points because people is really stable there.
Okay. So also in the chat box, Cara has a question for you. So your delivery reminds me of travel behavior expert from Chile, Sergio Heredias. Do you know him, perhaps? Yeah.
Yes, I know him. I had the pleasure to meet him personally last year and this year also. See, he's a really respect professor in Chile.
And he's a radio personality, so you may
Also,
want to tune in. He loves music, and it's just so nice to listen to as he talks about, whatever. It's wonderful. So I hope you guys get to connect again.
Thank you.
Okay, do we have any other questions from the audience? So thank you, Renato, for the talk. So we will move on to the next presentation, integrating instrumental, hedonic, and symbolic factors in interurban transport mode choice using psychophysiological and visual context indicators. So,
Hi, can you listen to me?
oh yeah, we can hear you.
Okay, great. Let me see if I can share my screen. There we go. Can you see the screen?
Yes, we can see your presentation.
Okay, great.
But it's really hard to hear you, so we're all going to have to turn up our volume. Perhaps you can put the microphone closer to your mouth.
Oh yeah, hang on.
Thanks,
Let me
Pablo.
see if I can. What about now? Can you listen to me better?
I think we're going to have to turn up our volume. And you're going to
Maybe
have to...
speak up a bit.
Yeah, no, sure. What about now? That's better?
Much better for me.
Okay, so it was just my volume, not the, the microphone volume. Okay, so yeah, sure. So hello everyone, my name is Pablo González. I come from the University of Chile, and I'm here to present my my investigation, which is called Integrating Instrumental, Hedonic, and Symbolic Factors in Interurban Public Transportation Modal Choice, using a variety of indicators. So, first of all, what factors do people considering when choosing between public transportation modes? We know the big ones, so time and cost, that's always there, that's always important. But there are also some other things, like, for example, how crowded the scenery is, or how safe I feel inside the public transportation mode, or some things that are even more subtle. So, for example, what can I see outside of the public transportation mode? So if I can see a beautiful scenery outside of the train or the bus, or whether or not I can do something else at the same time. So if I can read or do work, etc. aboard. Now, in literature, we have seen these different factors that I explained before, clustered onto three big groups. So instrumental factors, which are things that we can actually measure. So for example, travel time, cost, variability of travel time, regularity, egress times, etc. But there are also these two other clusters that are here, which are a bit less clear. So for example, hedonic factors, so which are related to emotional responses, so how stressed I am aboard, or how happy it makes me to travel by train or by bus, etc. But also symbolic factors, which are related to what do I think about when I think about the bus, what is my political view or my socioeconomical view about the transportation. So for example, if I think that the trains are the future of the country, or things like that. Now, we know that these two last factors are really hard to measure or hard to quantify, because how do you measure, I don't know, political views? It's really, really hard to get the essence of that. One way, which is the traditional way, is using traditional questionnaires. So, for example, Likert questionnaires and trying to do SP questionnaires to try to get, a sense of how people are reacting to crowding, or how people think when they think about public transportation. So for example, if people should take greener transportation, or what their view is on trains and that. But we know that these methods have their limitations. So we know that this doesn't really represent what the person aboard the public transportation mode feels. So what can we do about that? Lately, some new technologies have been introduced. In particular, here I show two that we're gonna be talking about on this presentation, that can help us to maximize the realism towards any choice models that we do, or towards any demand estimations that we do. So first off, here are on the left psychophysiological indicators, which are measurements of the physiological responses of people aboard trains, or aboard buses, or aboard public transportation modes. So we can actually measure when people react to different stimuli. So for example, the classical example is, I don't know, when I get scared and my hairs, they all stick up. That's actually a signal that we can actually measure. That's electrodermal activity. So we can measure these different signals, or when, for example, heart rate goes up when I'm scared, or when I'm stressed, for example, and we can try to estimate a different sort of instant utility, so to speak, along the trip. So how stressed I was, how happy I was along the trip. And another way that we can actually measure these hedonic factors, which are a bit more complicated, is trying to interpret what people see. Not only what people feel, like physiologically, but what people can see with their eyes. So this being the external environment. So for example, here I have a picture of what you might be able to see on a train trip, the train track and everything. And we have lately, with the AI boom and everything, we have different ways to try to get objective data that we can put into models from this picture, for example, what people see. One of them is trying to use an LLM video descriptor, which is basically just telling a large language model like ChatGPT or Claude or Gemini, here you have a picture, imagine you are a commuter, give me some scores of how scenic do you see, or how safe do you feel with that given picture. And we can also do something a bit more objective, which is basically give this image to a segmentator model, which basically tells us the objective percentage of how much sky there is, how much vegetation there is for each frame of the video of the trip that we see. And we can see those scores. So the idea is to try to quantify the impact of all of these different factors, so the instrumental that we can measure and the hedonic and symbolic, which are the harder ones, using all of the above mentioned techniques. So LLM image analysis and psychophysiological measurements, which is basically this. So we're going to try to enhance and stated preference base questionnaire with all of these psychophysiological data and with the video analysis that we did with LLMs. We're going to try to estimate those enhanced hybrid discrete choice models, so latent variable models, to try to get to the conclusion of which factor plays a role, etc. So we start with a base model. So we have a base model which is only estimated given an SP questionnaire that we're going to see later. So here's a latent variable model. Here are the latent variables. We have a latent symbolic construct and a latent hedonic construct. The symbolic construct, as we said, is related to political views on transportation. So, for example, I believe, here are the indicator equations. So I believe trains are the future of the country, or I prefer sustainable modes, or my mode of transportation says something about who I am. And we have the hedonic construct, which is related to experience on board. So, for example, like cleanliness or climate control makes the trip more present, things like that. And we also have the instrumental variables, which are the variables that we all normally measure on an SP questionnaire. So, for example, the headway, the travel time, etc., etc. The question is, how can we enrich this integrated choice latent variable model using the above mentioned data? So one of the ideas is let's try to enrich it with the visual indicator. So let's only focus on what the person can see and see whether that moves the needle, so to speak, if it can correct any biases or things like that. So how we're going to do that? We're going to apply it to this case study, which is near to where Renato was presenting. Here's Santiago, which is the capital of Chile, and here's Rancagua, which is a regional capital. The idea is that we're going to have participants travel between these two cities. There are some stations, but the most important thing is that the modes that are here, which are rail modes and bus modes, there are small buses and big coach buses, they have comparable standards of service. So the times of arrivals and the geographical position of the corridor is basically really similar between one and the other. So what we did is that we sensorized 30 participants with this little sensor bundle here, so to speak. So it's a wristband that can measure all of the above things, so the electrodermal activity and heart rate and everything. And we send them to do some trips along the corridor. What they normally did, we only asked them to do a minimum of one trip on each mode, but they could do 10 or 20 as they normally would. And we also took a stated preference survey, and we applied it to not only that 30 participant sample, but also a bigger sample to try to see if we can enrich the bigger sample with the measurements of the smaller sample. So here are the results of the bigger sample ICVL model. So we see that here are the structure equation results. We see that the signs are what we expect, and nothing really new here. But there is one thing that we can observe a bias on the constants. So here the train constant is the one that is fixed, and we see that both constants that are related to bus-related modes, so the coach buses and the Mitras, which are the rural buses, have a bias. So people prefer the train. This has been observed in literature as called the psychological rate factor, and we see it represented here. And we also saw, because this is a latent variable model, that in the latent variables there is a symbolic affinity that penalizes coach buses. So people who have stronger political views on transportation don't really like coach buses. But in general, people who have views that public transportation is really related to the comfort that they experience along the trip, they have positive hedonic affinity towards these coach buses. So what we also did is, well, then can we enrich this? How do we enrich this? We need some indicators, right? So where do we get these indicators to enrich this initial SP study? Well, we did a visual corridor characterization. So we tried to characterize all of the corridor, and we tried to do this segmentation analysis on all of the different frames. So we segmented the corridor on 100-meter intervals, and we took basically a frame of travel on each one. And here is, for example, the graph of, this is the kilometer 0. So here is Santiago, and here is Rancagua, and here is the percentage of what people can see on each one of the modes. So we can see that in general, in train-based modes, people can see more vegetation than in bus-based modes. And also, we can see the difference on, for example, that maybe on the bus they can see a bit more of the sky, because there are many things right beside for example, the train line versus the bus line, and things like that. So when we aggregate these scores that we calculate and we integrate it to the models, we see that there is actually a readjustment of the constants that we saw, of the bias, the psychological train factor that we saw. So this could lead us to believe that maybe part of this ASC bias towards train maybe actually just may reflect unobserved visual quality along the corridor, and could be explained for people just being more open to taking the train because the train is more beautiful or has more beautiful views towards the outside. So that's with the visual side, and here's the psychophysiological side. So we collected some data, some psychophysiological data along the corridor. Here's an example. Here's also the corridor, and here's of a person going along the corridor with the sensor. We have their heart rate, their skin temperature, the electrodermal activity, and we also asked for some emotions. So the people stated emotions along the corridor every 10 minutes. And with that, we saw some interesting correlations, which indicates that uglier scenery, so uglier outside scenery, uglier in the sense that more industrial, so more built, a bit more run down, so to speak, correlates with higher physiological responses. So people who see outside a bit more run down neighborhood or things like that, or things that are a bit more ugly, they tend to have higher EDA responses. So they are a bit more stimulated. And we can see that, for example, on some of these hotspots that we saw, actually we can see that it isn't really that beautiful. You cannot see that much nature, especially on the train side, for example. So this is quite interesting, because we could actually potentially integrate this into a model, which is the idea from now on. The idea is to try to integrate this into the model that we have before, and have a model that not only has the video enriched model that made us, lower that bias a bit, but also have different indicators. So trying to incorporate all of this, the skin temperature fluctuations along the trip, and also the heart rate fluctuations along the trip, and the electrodermal activity fluctuations along the trip, to try to get to better refine this latent hedonic construct. So we have currently we are taking data to estimate this. We have some ideas. For example, one of the things that we can try is to characterize instant utility, which is how the people feels, and calculate a score of utility for each one of the segments of the trip. So basically a continuous utility. We also are working with aggregate scores. So we're seeing if what the person remembers from the trip as an aggregated has something to do with how the person chooses on the SP questionnaire. And we're also working with susceptibility indices. So, for example, if a person is a bit more sensible or sensitive to fluctuations on the environment or things like that. So, to finish off, we saw that adding the visual segmentation indicators actually improved the interpretability of the model. We could see that the systematic train bias that was explained got a bit reduced. We saw that emotional responses show really interesting correlations that could be used further with the scenery outside. And we are currently working on the full integration of both the visual indicators that we just showed, and also the psychophysiological indicators. So yeah, thank you so much for listening. I don't know if somebody has any questions or.
Have we lost the chair? Samia, do you have some questions?
Oh, sorry, I was muted. So we have one question in the chat box. Do you want to respond to that? So since street vendors on board are not statistically significant here, do you think that reflects a genuinely weak effect or limits in how that attributes was represented in the experiment?
Sorry, I was muted. Yeah, so we put street vendors there because we did some focus groups before to try to make the SP experiment. And we saw that some people have very strong reactions to street vendors that get aboard the streets, and that's something very common that happens here. But in general, we saw that didn't really move the needle that much. Maybe because these strong reactions are getting, mixed up with some people who are not that biased towards street vendors or things like that. So, yeah, we don't see it as something that crucial inside the model. It's just we added it because it was important in the focus group and it came up.
Okay, so I guess that his question has a second part. So were the psychophysiological spikes more strongly associated with negative stressors like crowding and noise, or with positive stimuli such as scenic or engaging environments?
In general, with negative stressors. So especially for example, when reaching cities or when reaching stations along the corridor for the train side. Because the train stops in some stations, so when people come in and they crowd the train, there are some really marked FASIC EDA spikes. So that's the most common one. Normally, when we see, for example, the parts of the trips that are more like there's beautiful scenery outside and there are no stations in between and things like that, the person tends to stay flat, the EDA and all of the indicators. So it's a bit more calm.
Okay, so thank you. And we have one more question. Do you expect any resistance to labeling areas as unpleasant in the existing or future scenarios?
I mean, yeah, they're all of these things we labeled from LLM labels, so we know that LLMs have biases and that we are representing the LLM biases. We did some ecological validation of the labeling of the LLMs. So, for example, we took some example areas and we sent them to different students here at the university, and we told them, you have these ranks and try to score them, and we saw that they were really basically the same as the LLM set. So there's always resistance when you're calling a place ugly, so to speak. But But you could say, you could also use the other way of looking at it, that uses the more objective, so to speak, segmentation, which is, it's not really ugly, but it's like built up. So there's not much to see. There are only buildings and things like that. And we saw that this bias got smaller with both indicators, with the objective and the subjective indicator.
So I have one last question myself. So when you were adding these psychophysiological and visual indicators, did you actually expect to be able to improve the prediction of the mode choice, or just mainly you thought that these could help you explain why people prefer one mode over another?
It was more on the second part, so it was more of an explanatory thing. Because
Okay.
for prediction, each individual is different, so it's a bit more complicated. We only have to take, the things that are more instrumental. But on an explanatory sense, I think it's quite interesting what we read.
Yeah, definitely. Thank you so much.
Thank you so much.
So let's move on to our next presentation by Baldev Giri on Beyond Household Vehicle Ownership, Developing a Person-Level Car Access Index.
Yes, I'm here. I'll be sharing my screen. Do you see my screen?
Yes, we can see your slide. Are you ready?
Yes, I'm ready. Hello, good afternoon, everyone. My name is Baldev Giri. I'm a PhD student at the University of Arkansas. And today I will be presenting our study titled Beyond Household Vehicle Ownership, Developing a Person-Level Car Access Index. We conducted this work together with my advisor, Dr. Suman Mitra, and my lab mate, Arna. And the central question we're focusing on here is whether living in a household with a car necessarily means that every person in the household has the same access to it. So as we all know, in automobile-oriented transportation systems, access to a private vehicle is not only about convenience. It shapes daily mobility, access to opportunities, broader well-being, and it affects a lot of activities, out-of-home activities, breeds employment opportunities, maintaining social connection, and such. And in US context, this is especially important because roughly 92% of households own at least one vehicle, and automobile account for more than 87% of all person trips. So access to a car remains one of the most important determinants of individual mobility and accessibility. And most transportation studies previously do not directly measure car access at the individual level. Instead, they usually rely on household level indicators such as the number of household vehicles, vehicles per household member, vehicles per licensed driver, and categories such as carless household, car deficient, or car sufficient household. And these measures are useful at individual level, at household level analysis, but for individual level analysis, they share an important hidden assumption. They treat household vehicle resources as if they are equally available for all household members. For example, if a household is car sufficient or car deficient, this assumes that all members in that household have equal car access. For example, if in a household, if there is one vehicle and person A can drive, but person B is not a driver, these measures assume that both have same level of access. In reality, people in same household can have different level of access depending on whether they can drive, whether the vehicle must be shared, whether there is household level support from another household member. So prior studies show that vehicle ownership and effective access are not the same. and that restricted access can exist even in vehicle-owning households. Some other studies show that vehicle access is negotiated within a household through work schedules, household roles, caregiving responsibilities, and licensing status. So the literature clearly recognizes within household differences in car access. However, the gap is that there is no previous studies which has translated this within household differences into a transparent, continuous, and survey computable person level measure. And that is the gap we are trying to solve here. Prior research has established that these things, but we are defining car access here as an individual's practical ability to use a private motor vehicle when needed or desired for travel. And the index, which represents average car access, is termed as car access index. The important point here is that access is not same as ownership. Household vehicle ownership tells us whether a mobility resource exists in the household, but person level access asks what level of car access does an individual have. So here you can see the conceptual framework we used in the study. At the top, we have car access, and we have car access for drivers and non-drivers. For drivers, the car access depends on vehicle sufficiency in the household, driving capability, and support, whereas for non-drivers, the access comes from the household vehicle sufficiency and support because they don't drive by themselves. And further, we have distinguished the driving capability as having drivers with restrictions and without restrictions. Here, I have shown the calculation of operationalizing of different components of the car access index. First is car sufficiency. Car sufficiency is represented as C, and it compares the number of household vehicles to the number of licensed household drivers. Driving capability is 1 if the individual is licensed, and it's 0 otherwise. Household support is defined for drivers and non-drivers. For drivers, the support is 1 if there are at least one another driver to support. And we have also defined it for non-drivers. For non-drivers, support is the ratio of number of drivers to the number of non-drivers, because the drivers provide support to non-drivers.
Baldev, everybody's wondering whether you can show this as a proper screen rather than your entire, I guess, your own screen. We'd like you to go into presentation mode, please, using that lower right option. It's still very small on our screens. You're not able to use our space properly.
Okay.
I think that will work. I'm not seeing the left side, but oh, there we go. Thank you.
Okay. Do you see it now?
Yes, that's beautiful. It's much easier to read now.
Where was I? I was here. Yes. And yes, after the, here is the operationalizing of the car access index components. We have like 3 components here, like I defined. And after that, here is empirical calibration of the car access index. What we have already done is we have already defined different car access index components. Car access index components, but we also need weights. So for the weights, I used 2017 National Household Travel Survey dataset. and I used weighted average daily car trips as a calibration outcome. Here, the calibration logic is we first define the logical access scenarios. I here separate non-driver and driver pathways. Then I computed different observed car trip rates. I'll show you the logical typology I have here. And then I convert the stepwise differences into the car access index weights. Here you can see the logical typologies for deriving the car access index component weights. Here it goes from the baseline condition to the maximum access condition for both drivers and non-drivers in the household. And accordingly, we have computed the support for non-drivers and support component for the non-drivers, the vehicle sufficiency component. And for drivers, we have computed the vehicle sufficiency component, the weights for the driving capability component, and all of that. And lastly, here I have shown the equation for non-drivers and drivers. For non-drivers, car access index came out to be 0.23 times the support and 0.22 times the component household car sufficiency component, which means that there is like support and household vehicle resources. They are contributing equally to the car access index. Whereas for drivers without restrictions, support plays a very small role, and maximum role is played by the household vehicle component, and 0.26 is the weight for drivers, driving capability itself. And after operationalizing the car access index and after deriving the weights, I evaluated it, and we evaluated this through internal validation, and where we had synthetic household scenarios, and we checked through the car access index through these different validation components. Along with that, I also categorized the car access index to different groups: low, medium, and high car access index group, and I found the determinants of CAI, like who has higher car access than others, based on fractional logic model. And as part of validation, we compared the models of car trips and BMT for different of the previous conventional measures, and replacing them with the developed car access index. So what does low car access actually looks like? Here, after categorizing car access index into individuals into low CAI groups, medium CAI groups, and high CAI groups, we looked into different descriptive statistics component. And when we looked into daily car trips and daily BMT miles traveled, daily car trips came out as expected. It came out to be lowest for low CAI group, highest for the high CAI group. We also looked into their alternative modes uses, for each of this group, and as expected, low car access index individuals used more transit trips, more walking and biking trips, and their total daily trips came out to be lower than the high CAI category. And the interesting result is 27.2% of the individuals of low car access index group lives in car-equipped household. So this reflects that household level measure can hide important disadvantage which can exist inside a household. Here is the result of fractional logic model. From the fractional logic model, we can see that as expected, licensed driver, the individuals who have a higher household vehicle count and workers, they have a higher car access index, whereas for others, per the individuals who have higher household size, for younger individuals, for individuals with a medical condition, for individuals with lower education level, they have lower car access index. And here is the validation results. Here we had the same control groups, and we same control groups, and we changed the conventional measures to a car access index. Conventional measures were a number of household vehicles per member, vehicles per driver, and we examined the model fit, and we found that including car access index in place of conventional measures, this gives the highest model fit. We did a negative binomial for car trip frequency, and for BMT, I used ordinary logistic regression, and in both cases, the model fit improved when we used car access index in place of other conventional measures. Although the model fit for BMT is relatively modest, and although car access index was meant to be individual level measure, person level measure, we also computed household level car access index by taking the mean of each of the individuals in our household, and we examined the model fit, and it also gave better model fit. Here you can see R square for household car trips. It's highest in comparison to others, and it came out to be same for household BMT as well. The AIC, BIC values were also smaller. So what do this finding mean for measuring mobility disadvantage? So first, car access is a person level capability. It outperformed the household vehicle count, vehicles per member, vehicles per driver, especially for car trip participation. We found that even if the individual is in a car equipped household, which is more number of vehicles than the number of drivers, but there might be low car access in the low CI individuals, which is 27.2%. And this car access index can indicate unmet mobility needs, because we looked into alternative modes, and alternative modes partially compensate, but it do not fully remove the mobility penalty, because the total trips is still smaller than the higher CAI categories. So it will help identify, car access index will help identify individuals with low access inside vehicle owning a household. It will, and we can focus, we can plan for increasing the reliability, safety, and accessibility of non-auto modes if we utilize this index at spatial scale and find the areas which might be car equipped, but there exists significant number of low car access and low CAI individuals. So there are some limitations for this study, because we derived the weights only using 2017 NSTS. Local calibration can be tested. In regards to access mechanism, we did not consider external ride hailing, car sharing, borrowing, and day-to-day vehicle allocation. Future studies can consider that, and it measures car access, but it does not explain every determinant of the access. For example, like household schedule, one person being worker, another being non-worker, and these kind of things. But we were able to develop a new novel car access index, which measures person level car access, and it performs better if we are doing the individual level model, and if we replace traditional conventional model measures with car access index, and it can help identify a disadvantage in a car equipped household. Thank you. If you have any questions, please let me know.
Do you have any questions from the audience? You can unmute and ask the questions. Okay, so we have, yes, Paul, you can unmute and ask your question.
I don't think most people can unmute. Sana, you're just made a co-host. That's why you can do it. So you'll have to unmute.
Okay, yes, I'm able to unmute it.
Yeah. We can hear you, Paul.
All right. Thank you. Thank you. Thank you for the opportunity. Thank you so much, Giri.
Okay.
Quite an interesting work.
Yes.
Can you hear me?
Yes, I can
Can you
hear
hear
you.
me?
Yes.
Yeah. Can you hear me?
We
All
can
right.
hear
Okay.
you, Paul.
Thank you so much. Thank you for the presentation. All right. Thank you so much. It's quite interesting. I'm curious to see how you formulated this problem. Do you think all the there's noise from
Yes, I'm hearing you. Yes.
the
We can hear you. There is.
other side? Do you think the respondents were actually captured?
Uh,
I think income attributes. I think attributes. I think attributes like level
I
of
can't hear you
education,
clearly.
household size, income. I think this would have X. I don't know. I'm just asking.
I'm not clearly getting the question. Could you
Can
please
you
say
Can you
repeat
it
hear
your
one
me?
more
question,
time?
Paul? You were cutting off. We can hear you now. Okay, maybe we can hear his
Yeah.
question later. So we have one question in the chat box. Do you want to answer that first?
Okay. Do this
So,
CI?
do its CAI groups remain distinct after controlling for income, household structure, and neighborhood built environment?
Yes, I included income household structure, but I did not include built environment characteristics except for urban rural variable. But after controlling that, these remain distinct even in descriptive statistics and even in fractional logic model.
Okay, and one more question. The VMT gains are smaller, but still best for CAI. Does that suggest CAI captures trip making better than distance travel? How do you interpret that difference?
Yes, actually, yeah. I think since the BMT gains are smaller, so we can infer that it captures the number of trips better than BMT, and partly it might also be due to BMT is like vehicles mile traveled, and it is also influenced by external built environment factors, which we have not considered, and BMT is more influenced by outside built environment factors more than the number of trips, I guess. So that might have been leading to this smaller gain. But yeah, that's a good question. Thank you.
So I think that Paul was able to type in his question. So he's asking he's saying that his question is about.
Can I say something? Sorry, I went off.
Of course, you can go ahead.
Yeah.
So Paul, okay, I can read his text. My question is about incorporation of other demographic attributes like level of education, income, household size, etc. So do you want to talk generally?
Like the car access index itself, the way we have designed is meant to capture the average level of car access for different kind of individuals in a household. And I later conducted fractional logic model to examine the factors that can influence that actual average car access. So from fractional logic model, I have incorporated these demographic attributes like level of education, income, household size, but the calculation of car access index itself, it does not consider this.
Okay, thank you so much. So to not fall behind the time, we will move on to the next presentation, but please feel free to contact our presenters if you have more questions. So our next presenter is Chenyu Yuan. His presentation is on flattened preferences, distributed distortion in LLM-inferred responses for stated preference surveys. If
Yes.
you're ready, we can
Yeah.
hear you. Do you want to share your presentation?
Yes. So, hi everybody, I'm Chennyu Yuan, and I'm from Institute of Transportation Studies with University of California, Irvine. And my advisor is Matt Dean, which also is a professor at UCI. So my presentation today is about flattened preference, distributional distortion in LLM-inferred response for SP surveys. So the first topic I want to introduce is large language models are entering survey-based travel behavior research very quickly. So previously, state preference data have been experiencing some shortcomings, such the respondents may not fully understand novel attributes such as smart charging or any new technologies in transportation. So they may provide unrealistic responses, or they strategically signal social desirable values such as less pollution, more environmental friendly, and more curious about the new technologies. So large language model in another emerging tools help to validate whether the data is false positive or false negative. So they are more increasingly being used to help the state preference data to be more improve the quality. So on the other hand, large language model can be the synthetic agents or the synthetic respondents to enrich the state preference data, because it's really hard to collect thousands or millions levels of the data, but large language model can be the synthetic agents to enrich the incomplete survey records or to infer the attitudes and the preference, simulate the response, and support the behavioral modeling. So the central question of my topic is whether large language model can reserve or to preserve the behavioral heterogeneity observed in the human data. So there are many researchers nowadays, they are talking about using large language model to do the imputation or or look them as synthetic agents. So there are researchers that they are doing trust prediction or persona simulation or synthetic respondents. But the main evaluations they are using is either accuracy, means that how large language model can predict the goal output, or they are using some aggregate level evaluation to see how the choice shares are similar to the human respondents, or other evaluation like how VOT to income is correct or not correct. So all of them does not capture the variation across the individuals and demographic groups. So that will be a limitation nowadays. So our research here, we want to address three gaps. The first gap is that the measurement gap means that the existing transportation studies, they do not evaluate or they do not quantify how the large language model-based survey preserves the original distribution state response. And the second one, we want to show that different pumping strategies, how that will influence on the response of large language model, because the way you input the text and the information is very important nowadays. There are many different pump designs and pump technologies to help the large language model to get more accurate data. We want to test that in some most popular strategies to see how it differs from each other. And the third gap is that the equity gap, that existing studies, the lack of subgroup and intersectional evidence on how large language model outputs could compress the heterogeneity or suppress the extreme response. So we want to quantify in a subgroup level for large language model response. So the data we use is from a US smart charging data set with a previous paper published by my advisor, Professor Ding and Professor Kokelman in 2024. So we use the national survey with 922 US adults, which is collected in late 2022. And after that, we clean all the data. We use about 800 respondents for the aggregate distribution analysis, and 700 complete cases for the order logic estimation. So the large language model inferred outcome variable is a smart charging interest on a 5-point Likert scale. So this data set includes different size of the variables or the attributes from the respondents, including the demographics, the house situation, and the vehicle ownership, and also the charging location preference, environmental attitudes, and the lifestyle. Other prompt strategies we are using is zero shot, chain of thought, and self-consistency. They are looked as the most popular prompt design nowadays, and we apply that to 2 different large language models. The first one is GPT-5 by OpenAI, and another one is Kimi K2.5 by Moonshot AI. They are all assessed by GPT, which is UCI-sponsored licensed channels. So it's pretty much a close way, pretty much a low-cost approach to enable replication for researchers without large funding streams, because all is free for the UCI affiliates. So our 3 prompt designs included the same headline, which introduced large language model to think about you are a smart charging adoption analysis, and your task is to predict the smart charging levels, and don't include any historical patterns or any memories from previously. And how to predict the smart charging level is based on the 5-point scale. And to explain what is smart charging, so we give large language models the definition of smart charging. So the differences is the design of the prompt engineering. So the first most common one and most popular one is zero shot, means that we do not have any step structure, and straight from the beginning to talk about the person's attributes, the variables, and to infer how the output looks like. So the final output will be simply as a smart charging interest level and as large language model. Why do you choose this one? So there's no aggregation or other technology used for zero shot. The second one is chain of thought. So within one call for API call with large language model, we ask large language model to have 3 different reasoning paths, and we will compare them, and we will ask large language model to compare them with each other for these all paths. And finally, we will have a score assigned by large language model itself to as a final conclusion about what is the smart charging interest level of that person and what is the reason of that. So the aggregation is most likely internal. So large language model will decide all the process by itself, and we will not do any other things for large language model and to collect the answer. For the self-consistency is more different. We will have 5 independent API calls, and we will collect 5 different scores like the zero shot, and we will aggregate by majority vote in the end. So means that within the 5 calls, which level occurs more frequent will select as the final response. And if there's any tiebreak or any situation like this, we will select the median from the 5 calls as the final response. So that's the differences between the 3 prompt engineering designs we use to the large language model. And for the baseline part, we also compare how the current tools are differ from the large language model, especially with this high dimensional data. So we use regularized ordinal logic regression to predict smart charging level as a regression method, and also 2 machine learning methods to compare. The first one is random forest, means that we build many decision trees from different bootstrap samples. And XGBoost means sequentially adding new trees, not building many trees to correct the errors made by previous trees. So there are three technologies as a baseline to compare with the large language model to see that how the current imputation methods different from the large language model as a new technology. So the findings, the first general findings is that large language model compresses smart charging interest level distribution. So from the left-hand side, you can see that the ground truth distribution of interest level is more like a bell curve shape, a normal distribution. So most of the people stick with the median level of interest. There are some 100 people in not at all interest, and extremely level 5 means it's also 100% with extreme interest for level 5. But the ChatGPT and also Kimi K2.5, they have a huge distribution distortion, means that most of the people are compressed into the median level of the interest, but they predict no people or few people within 10 people have extreme interest. And there's a more severe cases here with Kimi K2.5, means that with zero-shot pump strategy and self-consistency pump strategy, there's no people predict as extreme interest. So there's a huge differences, and the flattening effect shown by the large language model here. And as for the conventional imputation method, it also has the flattening effects on the extreme level of interest. So the level 1 is lower than the ground truth as well. And for the level 5 extreme interest, it's better than the large language model, but still not as expected. There's only 16, 21, and 52 with each conventional imputation method, but it's not reached 100 as the ground truth level of data. So distributional compression is a systematic phenomenon rather than a pump or model-specific issue here. So the three matrices we want to measure large language model subgroup predictions, the first two we are using is total variation distance and Jensen-Shannon divergence. So the first one, TVD, we are comparing the differences between the prediction distribution and the true distribution, and to get the difference between each level. So that's the first one. And the second one, the Jensen-Shannon divergence, we have a middle point of the two distributions, and our true distribution and prediction distribution will compare with the median point of the distribution, how much information is lost from the median point of the distribution here. So that's two distribution shape we want to compare overall magnitude of the mismatch and also the distributional curve shape. And the third matrix we want to use is tail loss. So it's very simple that we are comparing the true distribution of extreme interest level 1 and level 5, how much difference between the true distribution and the prediction distribution, and make the average of the level 1 and level 5. So that's another matrix we are using. So the first conclusion we want to show here is the accuracy between the conventional and the large language model imputation. So large language model imputation on the one side is not pretty much higher or superior than the conventional methods. So all the conventional methods are between 30% to 34%, but the large language model is with across the prompting strategy and the models are also between the 33 to 35%. So ChatGPT-5 is slightly better than other conventional imputation methods, but they are all keeping the same level. And we compare the TVD and the JS divergence with each large language model and prompting strategies in different groups. So from here, we can see that in some minority groups and also some major groups, large language, the ChatGPT's TVD value and JS divergence value are within the range of the conventional imputation methods. That means that they can reproduce the subgroup level distributions reasonably well and within the range. And we see that XGBoost, which is the conventional models, have the lowest TVD value, means that it has the best performance to preserve the shape of the distribution. And compare with the Kimi K2.5, we see that Kimi K2.5 have a poor ability or extreme distortion of distribution compared to other conventional methods and GPT-5. So the TVD values and the JS values are larger than other methods, and so means that it distorts the distribution more extremely than others. For the tail loss, here I want to show that comparing the large language model with other conventional imputation methods, we see the minority, which means the yellow arrow over here, which means the black group of the person with different level of education as the intersectional effects. It has a higher increase of the tail loss value from GPT and the Kimi 2.5 than other conventional methods, means that GPT and Kimi K2.5 have more severe flattening effect on the minority groups. Other than that, I think GPT-5 preserves more distribution in other groups, such as the Asian and also the white the race, and but for the Kimi K2.5, it has a general distortion effect on all other intersectional groups in these cases. So our conclusion here is that large language model imputation amplifies the disparities across different intersectional groups. So the third test we did in this research is we are comparing the outcome variables from ground truth and three different prompting strategies into the order logic model, and we will compare the direction of the coefficient and the magnitude of the coefficient and the significance of the coefficient. So we want to see whether the ground truth logic model and the large language model logic model have the similar reports of the results for us to analyze. So it's very important if we have so many synthetic agents in the future to come into our survey data and serve as a raw data to have to predict the significance of the attributes. So it's very important to see whether they are in the same whether they can have the same effect or the same coefficient. So we will see if they have similar signs, magnitude, and significance. We see that the behavior relationship are preserved. But if there's any inconsistent results, so downstream conclusions may be misleading if there's many synthetic agents coming to the raw survey data.
Sorry, Chenyu, are you able to wrap up in 1 minute?
Oh, yeah.
We are a bit over time.
Oh, okay. Yeah. So our conclusion here is that both models show that agree with gender male and low income people. They are more interested in the smart charging, or they don't have too much interest on the smart charging. But large language model on the other side have four fabricated spurious effects on the older people and high educated level people and two race groups of the people. So large language model can fabricate some spurious effects in these cases. And our conclusion is that the large language model do not preserve the behavioral heterogeneity, and distortion is demographically non-neutral. So the problem is that large language model, both of the large language model can fabricate the same effects than compared to other conventional models. So our conclusion is that large language model is not the resulting artificial average respondents could lead to less outreach and fewer incentives for the less represented groups. So if we want to use large language model to oversample underrepresentative groups, so the validation is very important. So there are other ways or other tools we can use it, but since that we want to use persona simulation or synthetic agents, so currently is not a direct substitutes. So thank you, and that's all my presentation here.
Thank you so much for your interesting presentation. So just for the information of the audience, Kara has shared some links related to this research, so you can make sure that you check those. So we have a few questions in the chat box. Maybe we can answer just one of them, and for the rest, please directly contact Chenyu because we are a little over time. So one question is that looking beyond accuracy, which approach best preserve the full response distribution and subgroup heterogeneity?
I think self consistency means that the most of the response agree with the interest level. So I think that's the least way, that's the least influence way to choose majority vote, because we want to choose the average value or median value, then it will influence by the distribution of the response, and that can lead to an inaccurate response in the final state. So I think majority vote is a better is a better tool to use here for self-consistency, and is also recorded by the original paper who proposed the self-consistency.
Okay, thank you so much.
Okay.
So we need to move on to the next presentation. The intention action gap in e-shopping, longitudinal evidence and predictive insights from latent attitudinal representations. So are you ready? Adedolopo?
Yes, please.
You can share your presentation.
All right. Okay. Can you hear me and can you see my screen?
We can hear you, but Chenyu, can you please make sure that you stop sharing? Okay.
I think the screen looks great for most of us, Sonia.
Okay, I can see it
And
now.
you definitely, stop sharing if you're trying to do that.
Okay. You can begin.
Okay, all right. Yeah, thank you very much. My name is Adedolapo Ogunbiri. I'm with Applied Research Associates, and this study was carried out during my time at the University of Arkansas under the supervision of Dr. Suman Mitra. And it's the study itself, it's mainly around online shopping and a problem that sits underneath a lot of forecasting problem. That is, we ask people how much they will do an activity in the future, and we build a forecast based on the responses, and they sometimes do something else. Stated preference surveys are usually the main way that we learn about how people intend to do things in the future that do not particularly exist yet. For example, trying to learn about a new mode or deploy a new technology. And then sometimes when this future arrives, people simply do not do exactly what they state that they would be doing. And so this study mainly is to look into how it concerns e-shopping generally and how it affects how people travel. And what we found is most times the mismatch that is usually found is not usually a noise, and it's usually systematic, measurable, and we can usually rectify it and find a way to use their intentions or whatever it is that is stated as an intention to accurately predict what they'll be doing in the future itself. Throughout this study, I would be making reference to three main categories of items under the e-shopping itself, since that is the case study of this particular study. And the chart to the left shows how accurate people are in terms of stating what they would be doing in the future, and what they actually did based on a breakdown of the different categories. And you can see that they vary widely. And it kind of shows why it's sometimes important to break these things down based on categories. The first is food, and it refers to ready-made meal that are usually ordered and delivered to respondents. And that has an accuracy of about 70%. That is when people were asked what's the frequency that they would be ordering items such as prepared food. In the future, the response that they obtain as what the frequency is matches what they've stated earlier. And the same thing goes for the goods category as well as the groceries category, which has the highest accuracy in terms of matching the intentions and the finalized action itself. And looking at what has been done based on literature, now this is not a concept that is unique to transportation. It's been studied across other fields itself. And some of the things that we intended to do in this particular study is how much of it exists within the high city mobility space itself. And also the use of a longitudinal study within this particular field that is making use of data that we can actually see the data points in time within the same group of people. The data set itself that was used for this study is the COVID feature panel survey itself, and it's a national household survey itself. By the name panel, it's panel survey. It's tracks the same respondents. That is the same set of people that gave response initially are still the same set of people that were asked later on. And this particular survey was collected in different waves. The first wave had about 8,000 observations, and these made up the final subsets that was used for all the subsequent waves. And the wave three itself was used as an outcome wave for this particular study because of the timeline matches exactly what questions we had interest in. And the final observation is also about 2,400 observations. And it's less than the initial wave. Like I said, all the other waves are subsets of the first wave itself, and it tracks the exact same individual across time. Now, how does the data that we gathered, how do they relate to each other? First, we have interest in understanding and seeing what the realized action is and how well it has matched whatever stated intention was given. And again, the questions were along the lines of e-shopping based on those three categories. That is, how frequently would you actually shop for these certain items online? And how well did you actually do that at the end of the day? So the stated intention is how frequent they would be doing it in the future, and the realized action is how did they actually do it in the end. And some of the other variables that were considered in terms of the data sets are the social demographic variables. That is, what's their gender, what's their age group is like, what's their location and income. And some of the other variables as well were like how their travel characteristics, and other variables that were particularly interesting that was used are also the attitudinal variables. That is, how is their attitude regarding ICT use itself? That is, are they comfortable even making use of all these ICT modes of ordering things online, as well as their attitude to travel, among others. And in the next slide, it shows what the breakdown is in terms of a descriptive analysis breakdown based on the categories and what is being seen that is for each of the different groups. So now this is for the food category itself of e-shopping. Based on the generation age split, what is the general population breakdown? And what is also the general population breakdown when we look at those that accurately were able to provide what their intention is, and those that actually did match what their intention would be, who are categorized as being consistent. While the other group, that is those that have a mismatch, were categorized as inconsistent. And making use of the generation age chart on the left as an example, you can see what the category looks like for the older people, which is being circled. And you can see what the difference is when you compare that to the consistent, that is, they have a higher representation when we look at the group that is consistent compared to the inconsistent group where you had more of the younger generation being represented, who are those that are highlighted in the red variant color. And a similar thing was also observed when we look at the student status, that is, people that consider themselves to be students were less represented with when we look at the consistency, that is, those that accurately actually were able to self-forecast whatever it is that they, in terms of food, and inconsistency, they had a higher representation on there. And when we look at the goods category itself, there is less variation across board compared to what we had in the food. And also this particular category of e-shopping had a less accuracy general overall in the sense. And looking at that of groceries, the interesting part of this is rather than having the difference across the demographics itself, it was more structural in terms of access to vehicles itself. And you could see the difference in terms of those that have more access to vehicles were more consistent compared to those that had less access to vehicles, that is based on their driving status as well as the ownership of vehicles. And now the method that was being adopted in this particular study is to try to predict the actual action itself from the intention. And we had made use of a generative predictive framework itself. And the use of the generative part, which is the use of a variational encoder, was to be able to learn latent embeddings from the attitudinal data that was obtained, in addition to the other data set itself, as well as the stated intention. Can we better predict what people will do in the future? And this is a simplified representation of the conceptual framework itself from the wave 1 and wave 3, and the attitudinal data sets being fed into the variational autoencoder, and measuring how well that actually reconstructed and actually represents the attitudinal variables itself. And predictive machine learning models, these are 4 classic machine learning models that are being used to compare with the direct stated intention. And the accuracy itself was majorly measured by 2 metrics: the F1 score, just to help see the balanced accuracy, the balanced between what has been measured, as well as the direct accuracy itself, which directly measures how much representation it is from those that are accurate and those that aren't. And some of the results from, now this is from the variational autoencoder itself, it generally just shows how well it's actually trained based off of the attitudinal variables that were fed into it. And it did show that we had a good learning from that, which was then fed into the prediction itself. The next set of charts would be the final accuracy chart itself, being compared across the different models, again being compared to the direct stated intention. So for each of the chart that I'll be showing, the horizontal dark line shows what the baseline is, and the baseline is the stated intention itself. That is what would have been the accuracy if we had simply made use of the self forecast that had been provided in the initial wave, right? And we can see that for the food category, where we have about 0.752 when we consider that as an F1 score, right? And we have these 4 models. The first model itself was actually considered mainly to see the effect of a linear model. The other models are not essentially linear in the classic sense. And we could see that for the food category itself, there was substantial improvement in terms of the accuracy, both in terms of the absolute accuracy, as well as when we look at the weighted F1 score itself. And when we look at the goods, which generally has a very low accuracy when you look at the baseline itself, that is, if we had made use of the stated intention, we had an accuracy of around 0.45 itself. However, in introducing introducing the other variables as well as the attitude actually helped improve the score of this particular category itself. And a part of this that is interesting is when we look at the groceries. Now, these already had a very high accuracy itself. However, there was very little improvement compared to the other two categories that we had compared. And again, it kind of like validates why it is needed to actually consider some of these shopping goods in terms of their categories. And one of the reasons why this one had a very high accuracy to even start with is the way some of these products interfere with human lives generally. We observe that, I mean, generally groceries is a lot more routine-like to a lot of people, and so they have a better grasp as to how they could better respond to the questions as to how they are going to be ordering certain groceries in the future. And that kind of like, again, gives a reason as to why there is already a very high accuracy, mainly using the intention itself. And there's very, very minimal increments that was obtained from making use of these models included in them. And in conclusion, we were able to see that making use of this classic machine learning tools could help reduce the disparity and be able to learn more accurately what would happen in the future. And also, the intention action gap do exist within the e-shopping context itself. And more importantly, it does vary widely by the product category that is being observed. And the importance of attitudinal related variables itself is also seen in this particular study. And some of the practical policy implications would be planning to account for this uncertainty when we make use of this kind of intention or stated preference surveys. And again, we can develop models that could more accurately capture the gap. And lastly, as we saw in the description of the data itself, sometimes the mismatch could be treated as evidence or structural differences itself, just as we saw in the case of the grocery category, using that as an example. And what are some of the limitations for this study? First is the fact that we had made use of self-reported outcomes as well as in addition to the stated intention itself. It would be great to be able to have a situation where we could objectively measure what is used as the validation itself, that is the action itself, the measures of the action. So in this particular study, the action itself that is done is still self-reported, and studies have shown that sometimes there could be differences and errors in this. It would be interesting to be able to objectively measure this. Also, there is currently limited explanations on the disparities at this point for this particular study. And lastly is the categories that are considered. Based on what I shared, we had only 3 categories. One of the categories, particularly the goods, is a lot more robust and generic, and it could even be further broken down. And that could also help to explain why maybe there is a less accuracy in terms of what was measured by the stated intention. And that concludes my presentation.
Hey, thank you so much. So I guess that we can get one question from the audience. Any questions? So there is one question in the chat box. Which categories were hardest to predict? What do you think drives the differences? If you could answer very shortly.
Okay. So by prediction, the interesting part is based on the contribution of this particular study. I would say that is so I would answer that in 2 ways. I'm sorry. So others to predict generally, that was the goods category, and that had like the lowest accuracy, and that is also where the study had the highest contribution because we were able to move that from 0.45 to 0.7. And the second stage is in terms of what contribution this method had in terms of the groceries. It already had a very high accuracy generally from the stated intention, and we were able to only marginally improve that by about 2% or thereabouts. So that those are like the 2 interesting categories.
Hey, thank you so much. So
Thank you.
let's move to the next presentation by Mohammed Maliki, From potential access to realized travel, heterogeneity in healthcare-related travel behavior across transportation and socioeconomic contexts. Mohammed, you can share your screen.
Okay, can you hear me?
Yes, we can hear you.
And
You
you see
can
my
begin.
screen?
Yeah.
Okay, perfect. Good afternoon, everyone. My name is Mohammed Maliki. I'm a PhD candidate in transportation engineering at Southern Methodist University in Dallas. And for today, I'm going to present one of the pieces of my dissertation, which is titled From Potential Access to Realized Travel, Heterogeneity in Healthcare-Related Travel Behavior Across Transportation and Socioeconomic Context. This is part of a bigger chapter in my research, which is around healthcare-related travel behavior and particularly related to dialysis travel. And I co-wrote this research with my colleague Sam Purvadi and my advisor, Dr. Jenny Smith-Collin. So as I mentioned, the case study for this research is dialysis travel, and dialysis is a major survival issue among people who have end-stage renal disease or ESRD. Currently, more than 500,000 people in the US have end-stage renal disease, and because of that, they need to visit dialysis facilities 3 times a week, each session ranging from 4 to 5 hours approximately. And missing even a single session leads to major medical issues. And because of that, access to dialysis facilities is very important. And due to that, analyzing travel behavior of patients who visit these facilities will be important too. In this study, what we are going to do is to analyze how people who are living in different transportation and socioeconomic contexts visit dialysis stations, and what is the difference between their travel behavior and what is the heterogeneity. And by transportation and socioeconomic context, I mean the availability of transportation options that they have, the costs that they have to pay for transportation. And by socioeconomic context, I mean their income, their medical insurance status, and so on. We will get into that more information in the later stages. One of the ways to study travel behavior of patients is the idea of distance decay. And distance decay is the likelihood of visiting a facility with increased distance and how quickly it decreases. And the more quickly it decreases, as you see from the figure on the right-hand side, and the higher a slope that you see in a distance decay means that people prefer shorter distances or travel to shorter distances for dialysis. And if you see flatter curves for distance decay, it means that people travel farther. And the difference is in that we believe that it is different across different contexts, and it's not uniform across a city or a region. And because of that, it brings us to these 3 main questions that we are going to answer in this research. First of all, we want to see what are the spatial behavior and distance decay patterns across DFW, which is our case study, and also how it is different across transportation socioeconomic contexts. And then the concept of realized access, which is the actual travel time that people are spending going to healthcare, is different from potential access, or the matter of accessibility, mostly known as distance or travel time they have to spend on healthcare potentially, and how it is different from each other. As I mentioned, our case study is DFW region, or Dallas-Fort Worth Metroplex, and it is one of the fastest growing regions in the country with around 8 million, more than 8 million residents, and several counties that are in this region. And there are 172 dialysis stations there. And the workflow of the study and the framework is shown in the figure. First, I start with the data preparation, move on to the visit detection that I get into that, and then distance decay modeling and results and discussion. So first of all, in order to capture the distance decay, we need to know where people are living, what facilities they are visiting, and the time that they are spending going to those facilities. And for that, there are several ways of doing that, using surveys, doing interviews and asking people directly. But the way that we chose in this paper is using mobile trajectories. So we have a set of mobile trajectories across the DFW region. We track those from, for example, from 1 a.m. to 4 a.m. to see where people are living. If a person stays in a location for 70% of the nights in a month, we consider that as a home location of that person. And if a person's pink location intersects with the dialysis station and stays there for at least 1 hour, we consider that as a visit to a dialysis facility. And with those, we can capture the trips to dialysis. The other data sets that we have that we join to the land use of DFW are the transportation factors and socioeconomic factors. There are a lot of variables at the spatial level for transportation factors and also for socioeconomic factors that we join. And we merge all of them together, all those 3 data sets into hexagonal grid maps. So we can harmonize them into equal size or equal shaped hexagons across DFW, and each hexagon at the end would have the number of visits to a healthcare facility, to a dialysis facility, the travel times that people spend going to the dialysis facility, transportation status that could be the network quality, network densities, pedestrian network density, road network density, the walkability, the transit availability, the transportation cost burden and safety, and also their socioeconomic, which are the incomes and insurance coverage of the people who are living in those hexagons. And then in order to categorize those hexagons, there are 500,000 hexagons across DFW, more than that. In order to categorize them, we use clustering, and more specifically, we use k-means clustering and cluster them into different clusters. So each cluster could represent a level of transportation and socioeconomic status across the region. To determine the number of clusters, we use elbow method and silhouette width, and we determined that the optimum number of clusters is 3. And we divided this DFW region into these 3 clusters. So that we call them class 1, class 2, and class 3. But we need to know which of these clusters has the lowest status and which of these clusters have the higher status. So in order to determine that, we take the average values of each of the variables across the clusters, and when we compare them, we realize that class 1, for example, in the second radar chart, has the highest number of low-wage workers, highest percentage of traffic fatalities, highest transportation cost burden, and the highest number of people who live in zero-vehicle households. And when you look at the socioeconomic context, they have the highest number of people who are on Medicaid and Medicare, the highest number of people who have no insurance at all, and the lowest income overall across all the other regions. So we call that cluster the disadvantaged cluster. And class 3 on the other side, which if you look at the map, would be the areas with the darker blue colors, are the advantage classes that have higher incomes and better transportation. And the areas on the sides are the suburb areas that we call them middle class. They have the status that can be staged in the middle of between those 2 classes. And then with that, and using the trips, we calibrate the distance decays using different functions, and then fit those distance decays using regression, OLS regression, to determine the slope of their distance decay. So first of all, we sort the number of trips across different classes. And then when using regression, we can see that the slopes are very different. So class 3 has the highest slope as shown by the highest beta value. It means that the class 3, which was the advantage class, always use the people there usually use the closer facilities. The class 1, which was the disadvantage, people use the farthest facilities and farther facilities compared to class 3, and class 2, which were living in the suburbs, as shown by their distance from the city centers, they spend more time going to dialysis facilities. So in summary, what it shows is that class 3 has a steep decay. They met their dialysis locally. Class 3 has the flat decay. They're forced to travel longer distances, and they travel longer distances. And class 2 also has the flattest decay, and because of the distance that they are living from the dialysis facilities. But to look into more detail, we wanted to see what is the actual or what is the potential access versus the realized access. So we simply look into what is the shortest travel time to dialysis facilities on average in class 1. And we see that it is lowest across all the clusters. It is on average 4.24 minutes. But people are spending more time, around 14 minutes, going to dialysis facilities. But it is different in class 3, where people have a slightly higher average travel time to healthcare, but they are actually spending less time, around 10 minutes, around 4 minutes on average, less than class 1, going to dialysis facilities. And in the class 2, which were the areas in the suburb, distances is a lot. They are spending more time going to dialysis, and because they are forced to travel longer distances. So what we get from this, what are the key takeaways, is that, first of all, to answer the first question, distance decay varies systematically with transportation and socioeconomic context. In different contexts, distance decay varies. People are spending different travel times going to healthcare. And the longer travel times in disadvantaged areas may reflect necessity, not choice, because a lot of times people interpret distance decay as the ability of people to travel. And if they have flat distance decay, they assume that people are willing to travel that much distance. But in this study, since the socioeconomic context of areas that had flattest decay was the lowest, we can assume that it is because of the necessity due to insurance coverages of different stations, different facilities. And with that, we can infer the necessity of those travels. And based on that, we should target transportation support and facility setting where access is most constrained. Not only looking into the distance, into potential distance, but looking to more factors like the availability, like the station availability, insurance coverage, and so on. And the implications would be in the constrained areas or in the class 1, we can fund non-emergency medical transport, subsidized rides, or in the suburb areas, we can prioritize facility setting in capacity where services are spread thin, not just demand is dense, and also measure what people face. And we need to look more into what are the barriers instead of only looking into distance. So with that, I wrap up my presentation. I will welcome any questions or comments. Thank you.
Okay, thank you so much. Any question from the
Yes.
audience? Okay, so we can answer one question from the chat box. So one question is that you conclude that longer trips in disadvantaged areas reflect necessity rather than choice. What evidence in your analysis supports that distinction between constrained travel and voluntary willingness to travel further?
Mm-hmm. Okay, that's a very good question, actually, and this is what we are also looking more into in the next stage of the research. But what we understood was that people in the disadvantaged areas actually skip the nearest, sometimes skip their nearest dialysis station, dialysis facilities to go to the farthest facilities that have higher number of stations or have the higher number of or the most insurance coverages. So from that we can see that there are nuanced reasons that people travel longer, and there is actually a difference between those facilities, and they are not only skipping those because they want to travel longer, and that doesn't actually make sense if they want to travel longer if there is no difference between those stations. So, and since there are lower socioeconomic context and transportation context, we can realize that they are forced to travel those distances, otherwise they wouldn't have. And but we are looking more into that, and with the future research, we can answer that with more details. I hope this answers the question.
I don't know if there was anything else in the chat box there, but I think we have come to the end of the 5 hours today. So it's so nice to see you guys in here. So many of you are familiar to me, especially those of you sharing your headshots. Vince, I'm wondering where your headshot is. Yeah, and Victor's down, I think in Colombia, which just had a major earthquake. So Victor, I don't know if we can make you co-host, but I would love to hear more about that. Tomorrow we've got Marta Gonzalez from Berkeley presenting at what is 10 a.m. my time? Might be like 12 a.m. or noon, sorry, in Colombia. And yeah, if our tech staff person, thank you for serving in that role, can go ahead and unmute whoever raises their hand and wants to just chat for a bit. I'm here and happy to hear your thoughts on day one of our Western sessions. Of course, in about 6 hours, we have Tessa Sanchez, who is the head of sustainability for Uber, talking about electrification of their fleet of independent contractor vehicles. So the kind of charging and incentive programs they have in place around the world to electrify those vehicles, which makes them a more positive thing for our cities, given that they travel about half empty. So thanks for being here, everybody. Victor, I think I can make you co-host, or maybe I can't. Oh, let's see. Mubarak, are you able to make Victor our co-host? And if anybody else raises their hand, I think Mubarak can make you a co-host so you can unmute. Rob and Robert, nice to see you. Michael and Mike. Kitaro leading our tech team, and Suman leading the whole Western set of sessions really for us, along with Jean Parodi, who's at the University of Tokyo for the Eastern sessions. So Victor, you can unmute now if you're with us. It's possible he has walked away.
Jara, one quick question. What happened to the chair of this session? She left or there is some tech issue there? I don't know. So
No idea. I haven't heard from her. Yeah, she's a good friend, I think, of Mernaz Gamami, who created the program, and so she wanted to choose chairs that she knew well. I noticed on the slide that you have here, Juan Carlos Muñoz was Secretary of Transportation for the nation of Chile, and he is back at, I think, La Católica, which is a university there in Santiago. So we can add that to that slide in case you end up showing that tomorrow morning when you are kicking us off with our keynote for tomorrow. So Martha González, who's in California these days, I think. Okay, well, Victor has probably stepped away. Let's see what we've got in the chat box. Yeah, big thank you to Poria for always having a question for our presenters.
I'll update that slides, Kara.
Sure. Yeah, yeah. Well, I hope you all had a good time. It's nice seeing you all. And Suman, it's funny how you and I kept picking the same
Yes.
sessions to attend, and you had a couple students present and while I was listening in, so that's wonderful.
Yeah, I went back to another session and then I came back because that one I was co-host. Since I saw that you were here, so then I can leave. So.
Oh yeah, you can sleep easy when I'm in the room. I'll jump in at any moment, as long as they allow me to unmute myself.
Yeah.
Okay,
I think
get some rest.
today went well. I think we had in the morning, we had 118 at some point, I noticed, which was very good. And all the sessions on an average, I thought 20 to 35 I saw in the range. I'm collecting some data and I'll share with everyone later.
Yeah. I put my counts into an email to you and some others,
Yeah.
I think already. So yeah, it's been good. It's been a good experience. I think we'll go ahead and shut down this room now.
Yes.
So Mubarak and you can get some rest, and we'll see you guys tomorrow.
See you tomorrow.
Okay,
Thank you,
bye-bye.
everyone.